This is the Waves Homework Booklet question 33. We've got a student standing some distance away from a wall, clapping her hands. She listens to the echoes produced by the sound reflected from the wall and adjusts her rate of clapping so that each clap coincides with the echo from the previous clap. A fellow student counts the number of times she claps in 20 seconds, and it turns out she got 47 claps in those 20 seconds. First thing, simply calculate the time between two successive claps. So the 20 seconds we've got to share out between 47 claps, so it's 20 over 47, it's 0.43 of a second. The speed of the sound in air is 340 meters per second. Calculate the distance the student is from the wall. Do a simple speed is distance time calculation, but the distance is the distance the wave travels from the student to the wall and back to the student. She's clapping when she hears the echo, so the distance is to the wall and back. So it'd be speed times the time, 340 times the time from previously, 146 meters. Therefore, the distance to the wall is half of that, 73 meters. If you'd started by saying, well, I'm going at 340 meters per second for 20 seconds, and I'll divide that by the there and back factor and the number of claps factor, you actually end up at 72. So you can end up with either of those two numbers. It's just a slight rounding thing that happens along the way, not a problem. Student then goes to carry out a diffraction experiment. She stands on one side of a fence that consists of evenly spaced wooden strips. The fence behaves as a diffraction grating. See how important it is to read these bits of text. It's absolutely telling you where the answer's going to, what you're going to have to do for the answer here. She uses a loudspeaker to send wave of frequency 240 kilohertz, 2.4 kilohertz towards the fence. And first thing you've got to do is simply calculate the wavelength. Simple C equals F lambda, 340 over the 2.4 times 10 to the 3. Got to get that kilohertz in, looking after your powers of 10, 0.14 meters. It's interesting here that they've told you the speed of sound again. No need for them to have done that. They could quite reasonably have expected you to have picked that up from the previous part of the question, so that was nice of them. Diffracted first order maxima is at 28 degrees. Calculate the spacing between the adjacent wooden slits. So we're starting with d sine theta is n lambda, rearranging that for n, so I'll get n lambda upon sine theta. N is 1, so it's just that wavelength, 0.142 if you get the whole thing in, or a bit more of it in your calculator, divided by sine 28, and we end up with d as being 0.3 meters. Then we've got my favourite questions on these, which is to simply, what's the highest order maximum that we can get? The way to do that, we're trying to work out n, so we rearrange n lambda is d sine theta to n is d sine theta upon lambda. And we say that the biggest that sine theta can possibly be is 1. That's the same thing as saying the biggest theta can be is 90 degrees. Sine of 90 is 1. So the biggest possible value of sine theta is 1. So my maximum value of n will be simply d over lambda when sine theta is as big as it can be. And that gives me 2.14. But I can't have 2.14 maxima. I can only either have 2 maxima or 3 maxima. So we have to round down. If it's not exactly 3 or bigger, I can't get the third one in. So that gives me a highest order maxima of 2. So that was the homework booklet question 30, the Waves homework booklet question 33.